speaker today. And as I mentioned at the beginning, this is an ECE seminar, but also a guest lecture in my class called Optics for Energy. If you're interested in the class, you can check out my website. Kunjal will introduce himself shortly, but I just wanted to make a quick point that I've known Kunjal for many years, primarily because of a startup company that was spun out of the University of Utah about almost 10 years ago, maybe a little bit.
I know, yeah, it's been a while.
So I've interacted with him quite a bit, and but in the context of entrepreneurship. So this is a kind of an ideal. It's really great to hear from someone in industry, and I just want to mention two other things that Kunjal at that time, and I still think now, was part of a team working on how humans interact with computers, not only for displays, but for other things as well, which I'm sure he'll talk about briefly, but I just wanted to mention that. But of course, the interaction of human beings with technology and computers in particular involves quite a bit of optics. So that's why there is quite a bit of relevance to the class, to our class. Now, I should also point out that Kunjal is very much involved in doing due diligence, for instance, for Intel Capital, and has an MBA from the UC Berkeley and so on. So he's very much plugged into the entrepreneurial ecosystem as well. So there are two points of very close overlap with the goals of this class. And I'm hoping that you can take this opportunity to have a discussion and so ask lots of questions and learn quite a bit from Kunjal's experience. So Kunjal, it's all yours. Now monitor
wonderful.
Chat for questions.
Awesome. Hey, Rajesh, thanks for your generous introduction. Maybe first thing I should ask, can I take that class? That would be awesome. I would love to.
You can teach it.
So I can tell you folks, Rajesh is a great combination when it comes to one of the finest scientists in the industry, and also one of the best entrepreneurs that I have known. It's very rare combination. If you look around, I have seen people excelling in one over the other. And Rajesh sets a pretty a role model, at least to me, having known him for years. So thanks, Rajesh, for this opportunity. I hope I can live to the expectation, basically, on what you on your desired goal. And what we plan to cover today is going to be a display overview. And guys, look, I don't mean to take you or make you guys an expert in this field. It's a pretty deep field, very broad. What I wish to cover today is really, we want to start with an inspiration video, and I'll go through that, and really about the vision. Why display? I mean, displays are everywhere. We are seeing through one right now. But how it has changed us as a human being on how we perceive things, how we communicate, especially during this COVID times. It's our only mode of communication. And how the optical field has helped transform and shape that industry. So make it interactive, guys. I have a few questions, basically, so I want to make sure you guys are paying attention. There is a class participation grade that your professor would be grading on. No, I'm just kidding. Let's have fun. That's the goal. And feel free to pause me, ask questions if you want to make it interactive. All right. With that, real quick, I just want to give a little bit about myself. So on the left is really about my academic and my industry career. I have been in the industry for about 15 years. I'm a principal engineer at Intel. My career focus is really, I love to work at that junction of technology and products. I call myself to be a product guy, and at Intel and the industries I worked before at Samsung, at HP, and the startup I have driven, I've been fortunate to be working with a very smart technologist in the industry like Rajesh, and how we can go bring in some of this technology value proposition in terms of building up differentiated products. And we'll talk through some of the stuff I have worked on within the industry across my past career, and there is a lot to be done. So I'm looking forward to this relationship, this engagement. In a typical class environment, I would go ask folks more about the introduction, and especially to know more about you, especially on a fun fact. I have some stuff on my right. This is how I live every day. Basically, I try to role model. I'm not perfect, but just to give myself about like, hey, student always, I think Neda commented about being very open and learning about this new field. So thank you, Neda, for joining us. Family always comes first, especially in this time. Just to give you a bit about myself, this is a picture of my family just outside the Versailles Palace, just around this year in France. And who would have known the life would have changed so much within a year. So again, little bit about a fun facts. I can speak 5 languages. Again, as you can tell, I'm an Indian origin. I've lived in Korea when I worked for Samsung, been in this beautiful country for 20 years. So, that's one of the fun stuff I love to go and pick. So with that, let's get started here, guys. I want to share a video. This is a visionary video, not from me, but from Corning. And I'll keep my fingers crossed it comes through well across in the Zoom. But as you look through the video, it's about 10 years old. And this is the time when iPhones were just coming out. So it talks about the vision on what has happened since then and how much prediction was done. And you will see you're still halfway. So let me roll that up real quick to get us started here. Can you hear the audio, by the way?
No.
Okay. No, the audio doesn't come through. So I think you have to probably turn it up. I've had the same problem.
Yeah, let me do that. Give me a second here.
If not, you can just narrate it. Sportscast.
All right. I need to mute. I think you guys can hear echo.
Go ahead. I can hear you. Now you. Go ahead, Kunjal. I think you need to unmute your computer. You're muted, Kunjal.
All right, how about that? Can you guys hear me now?
Perfect. Yeah, go ahead.
All right, let me get rid of this stuff. Sorry about that. So how was it? You guys like it? This talks about if you go look at 10 years back in a history where the iPhones didn't even existed, and it speaks about the vision, which actually Conning put together, which acts as still one of the best visionary video for the industry. And I want to take you guys to a journey on how it all began, right? So these are some of the key milestones within the industry where basically we all know, and some of you guys may be too young to even remember about the CRT TVs, but when you look at the birth of the CRT TVs happened somewhere around that 1897. And that early part of 20th century was all about those big TVs that were first came to the life, right? Just around that time, about 10 years after, is we have this discovery of electroluminescence, which is a fundamental principle around how LED works today. And the invention about the LED came in around 1961, right? So, and then took the journey about how LCDs and plasma came out around those 1960s. And just about 20 years in a time frame where we got OLEDs. This is the technology we'll talk a bit more in a detail today, but now that exist in a pretty decent chunk of our smartphones. iPhone Pro 12 just got announced a week back, basically has the OLED technology. And I was privileged to start my actually career working on OLED with Samsung back 15 years back. So you race forward basically LCD technology. It's still a very dominant technology of choice, and that basically took away plasma. If you guys remember plasma TVs, those were like pretty thick, pretty heavy, gets too heated, and people just didn't like it. And LCD took over that market. So this was a time or a business inflection would happen around 2007 where LCD took over on plasma. And just around that time, the OLEDs were launched. So I was fortunate. This is a time where I joined Samsung around early 2000, and my job was basically take on some of the good inventions that were done on a technology side on how we can roll into a product. So just around 2008 time, I left the company, and coincidentally was a time when we launched the first smartphone into the market. And then came the e-reader, basically thanks to Amazon on digitizing an entire this reading economy. It was a technology being developed like probably about 50 years back, but until Amazons of the world came in to put it into a Kindle product. That's where the inflection of this technology happens. So the question really here moving forward is like, hey, what next? And we'll touch base on some of the aspect, in my opinion, where the things are heading, right? And it's a pretty fast-paced industry. The inventions happens fairly quickly, and I'm sure there are a lot of smart folks around, like the one in this room, can really create the history in this field. So with that, basically what I wish to cover basically in next few slides is really about some of the fundamentals. And we're not going to go through each and every individual technology, but I just want to break it down for you guys. Everything what you saw in that video was primarily, you can classify into two kind of a display technology. So one is emissive type, and the second is a non-emissive type. So emissive includes basically stuff like CRT was one of the golden example of an emissive display technology. LCDs today are non-emissive, and what does it mean is you need some form of a source or medium in order to pass on the information. They are not a self-emissive display, unlike OLEDs. So we will talk about OLEDs, organic LEDs, and we'll talk about the active matrix LCD technology. This too covers nearly about 99% of a technology that exists in our products today. So we'll dive deep into that, okay? So with that, let me give you guys a quick overview. So one on the top is really a high level breakdown of an LCD screen. Most likely if you're using a computer, you are looking at an LCD display. And fundamentally, basically, if you look at from left to right, the way the technology works is you have a backlight that goes through the series of optical films that get polarized in a certain direction. It goes through basically a TFT array. TFT stands for a transistor. So this is an electronic circuit that sits behind the glass. And then you have this liquid crystal. These are the magical crystals that basically depending upon the voltage of operation, they changes the shape and the orientation. And that's how the different light modulation will come through. And the color filter basically renders your red, green, and blue, and making sure that you have a good visual quality and your optics are not compromised. You have an outside polarizer. What I want to think about it, if you look at this problem, or I should call it as a technology that works today, about you start with 100% of a light, you are nearly giving away 95% of a light, and it still works. That tells you that there still exists a 95% of an opportunity to get this technology better. And there is a lot of work going on in that. We'll talk more about it. And this is some of the brilliant ideas and the startups that Rajesh has created in terms of helping and solving some of the issues like this. So, but I just want to keep you in mind, here is a state of art LCD display. It's a 95% inefficient, but it still works. That's what out in every product right now. The one at the bottom is basically I call out as an emissive display technology. So whether it's an OLED, X stand for basically OLED, and we'll also cover another technology called micro LED, which would cover at the end of a presentation. But this is nothing but an emissive display, just like your LED. You turn on the switch and the light will emit itself just like a light bulb. In this case, it gets a lot more sophisticated about you got red, green, and blue LEDs, and you got an underlying transistor as a backplane. So this is one of the emerging technologies. It exists today in bulk of our products now, especially the last 10 years has been an inflection point, as we spoke about beginning 2008, where this technology has grown bigger and bigger. And we'll talk over why on some of the fundamental benefit, especially on the visual quality and the thing you can make it flexible, moldable. You're seeing some of the phones coming out, like Samsung announced their flip phone. And there was a flexible laptop that came out that I was fortunate to work on a few weeks back. So we'll talk about that. But that's just in general, a real simple, a very high level concept between about the two technologies. Okay. All right. So breaking it down right into the pieces, like, hey, what it is. If I were to go break down my laptop and look at the display, this is how it would look like. So what you are seeing at the bottom left is basically this is your display panel. And what exists, there is a panel electronics board. There are set of interface basically that goes from the panel into your motherboard. And there lies basically the driver electronics, what we call as the source drivers and the gate drivers. Basically, these are nothing but the active drivers in order to go turn on your information. So you get all this video, the images, and the gate driver and a source driver are nothing but they are rastering, just like how in the CRT days, you raster the phosphor across the screen. Here you have electrons basically rastering across the screen. That's how you perceive an information. So a real simple electronics over here in terms of what the construction of a display screen look like. So going even a further step down, right? Basically about let's talk about LCD. and you go to the next level about, oops, I'm sorry. You go to the next level about like, hey, going to a pixel, what it is really, right? So pixel is basically the smallest spatial information element that you got. And you have what we call as a subpixel. This is a red, green, and blue subpixel, which are the fundamental primary colors that generates all the beautiful colors that are out there, the one what we could see. So that's what the definition is. And if you look at the construction, so before I take you to the more details, I want to give you a quick analogy about the shutters, right? The one on the right. So what LCD is really about, there is a light source, as you can see, a sunlight outside. And your shutters are nothing but the liquid crystals. So depending upon how much light what you need, you just go and modulate those shutters, and that's how you perceive the information. It's that plain and simple. A decade-long old technology, 95% inefficient, but it still works. And if you break it down, right? So what in the middle, what you guys are saying, basically you got this series of layers over here. You start out with the backlight module. You have a polarizer, you got the transistor array. So this is what we call it a thin film transistor. So this is like a 5-mass process transistor, extremely simplified version versus the kind of a transistor technology that Intel works on in a semiconductor are literally about 50 mass process, 60 mass process. The design margins, what we are talking about in a display industry are of the order of microns, versus if you look at the semiconductor, is the order of nanometers. We are talking about the 7 nanometer and 5 nanometer technology. So the question always gets asked about to me at Intel, since I work at Intel, like, hey, like 1 micron, 2 micron is way old as per Intel standards, right? I mean, why this technology is so critical and important, right? So you are talking about something which is 200 times less sophisticated just from a node perspective, a 5 nanometer node versus a 1 micron node. Why this is so important for Intel. So we'll explore that in a second, just after this slide. So keep that in mind about the technology of display in the order of microns versus semiconductor or in the order of nanometers. So give you a quick idea on the driving methodology, right? How does it work? So focus on the one on the left, basically. So this is an electrical diagram. Basically, you got a display screen which got a bunch of pixel electrodes and the transistor circuitry. So this is like a hold and sample type of a circuitry. You drive it through the gate drivers, the source drivers. You have a bunch of ASIC to go control the driver circuit. You have a DC to DC converter to make sure that you have all the power rails coming in. And at the end of the day, you zoom further in. The reason why we call it as an active matrix, because there's a series of pixels across the display. So this is how the anatomy of the different pixels look like and how they are connected. And you got a timing controller, basically make sure that, hey, you don't have flicker, you have seamless transmission between your source drivers and the scan drivers, and all the power operations are working well. So this is all about how good and how well you do the timing. So a real simplified version, but just want to give you a sort of a view about what exists in a display screen. Okay. All right. So let's explore that path about what I
Kunjal,
just
I had a
brought
quick
up.
question.
Yeah, please. Was there a question?
Yeah, in the previous slide, can you talk a little bit about the row column addressing, and is it global addressing? You sequentially go through each row, or is everything refreshed at the same time? How does
Wonderful.
it work?
Wonderful question. So the way it works, what we call in our industry as a raster scan. So what does that really mean is if you see my cursor, you start with the first row, you enable the first row, these are the serial drivers, and the source drivers are the parallel drivers. So you enable the first row and you plug it in all the information at the same time. And you repeat it sequentially, actually row over row, within a certain frame period of time. You don't want to see the information kind of filling in the spot as you're reading. Otherwise, it creates this perception, what we call as a flicker. So a typical frequency of operation is 60 hertz. 60 hertz is about the time wherein your eye integrates all that information basically, and you don't see the flicker. So your scan drivers are actually operating in that 60 hertz refresh rate time frame, and it goes row after row, and the source driver is bringing all the data into the information. So this is how this is how the data gets plugged in into the display screen.
So,
Does that
so
help, Rajesh?
yeah. So, but when you have big displays like TVs or advertisements, so on, this I assume the capacitance is a problem, right? Because you
Yeah, great
drive
question.
over. So how do you deal with that?
Very good question. And multiple ways. One of the most common ways is you actually break down the screen into half, exactly with your problem, what you mentioned, Rajesh, about because now you're dealing with the impedance issue, because now your information need to go travel longer distance. So what industry would do, especially when you talk about the bigger TV, they actually either break it down or slice it into half, or even go break it down into four zones, and you are actually scanning from all the four areas at the same time. What does that mean? Is you are scanning at 4 times the higher refresh rate now. So you need to have more sophisticated drivers and more sophisticated circuitry in order to go handle larger sizes like TVs and all. It's a great question.
Right. Thanks.
So let's kind of think about the question I asked about the 5 nanometer node that exists in semiconductor versus 1 micron in display. And when we talk about a display, I want to give you an idea about how in this industry the size matters. We don't scale in this industry below 1 micron, but we actually keep on scaling on the other dimension, which is basically a glass size. So everything in a display fab is been measured by what kind of a glass generation you're supporting. So here is an idea just for you guys to visualize, right? So this is a typical person, and what you are looking at today's industry have migrated over a period of time from a small size generation glass to right now at about generation 11 kind of a glass, which is a meter square. And to give you guys a perspective, this glass can handle about 865-inch TV or 200-inch TV. So this is how the economics work. Rather than scaling down in a dimension, it's all about an industry about scaling up. This is how the industry is able to bring the cost lower. So if you look back, the TV prices as an example, I bought my 55-inch TV about 4 years back, cost me about $800. And you go in a Costco today, you'll get it under $300 just within 3 years. And where it is coming from, and it's really coming from this manufacturing economies. So if you look on the right, I just want to give you guys a perspective, right, about this industry and the demand, what is being created. So this is an overall demand chart, basically, and the left is basically the billion feet square of a glass that get consumed. So I took an analogy, was trying to understand, hey, how can I put this 7 billion feet square in perspective of a demand that would be generated somewhere around this time in terms of building up all the devices of the world, all the display devices of the world, and that perspective about 2 times the area of Salt Lake City. So that gives you the scale of this industry on how big and wide it can go from the manufacturing perspective. Cool. All right. So guys, ready for a question? Thanks, Rajesh. So the question really, and again, this is, feel free to guess, right? This is in relationship of a soccer field based on the information I just shared, right? What do you think a typical size of a display factory should look like, right? Is it Is it a size of a soccer field, or 10 times the size of a soccer field, or 200 times a soccer field, or 2000x, right? So let's hear from the audience here.
Sure. Let's give it a couple more seconds.
Sure.
And I'll share the results.
Awesome.
We have a few more people to vote.
Hey, Kunjal, in the meantime, I sent a question in the chat. If you could respond to that.
Sriram, why don't you read the question too? It's
sorry, I didn't got a chance. Please go ahead.
Yeah, so no, can you comment on the typical pixel size? And then the next question is, you're talking about this 95% light loss, right? Is that related to absorption losses, related to transparency of the electrodes, the TFTs, and metallization, if there is any?
It's all at a first order absorption loss, basically. So, and that's drives one crazy, especially in the field. You got these different layers. Basically, you start from the backlight, then you have a polarizer. So polarizer are the most light cutting element. We are talking about an efficiency of the range of 42%.
Do you want to go back to that slide?
Let me do that while you take the poll. Absolutely.
Yeah, this is actually very useful if you want to.
Right. So you start out with 100% of a light. So think about it, 100%. And the polarizer takes off nearly about 50% over here, because you got to polarize in a direction so that it goes to the liquid crystals. So liquid crystals are a very homogeneous material, and you want to make sure your light directivity is not impacted when it goes through. And then you got the color filter, which are another 66% of an absorption loss that happens, because now you need to go and cut it down the wavelength, basically, for red, green, and blue filters. So that's where you get the other 66% loss. And then you got the end polarizer to make sure the directivity is conserved from where you started, which takes away another 50%, sorry. So you're looking at really about 5 to 8%. So if you look at a typical phones, if you're holding, that's about 5%. A typical TV, which is a very low PPI and will work to the definition, is about 8%, right? So
this is where polarized emitters and polarized. If you had polarized emitters, is that the direction in the future?
Right, exactly right. So there are tons of research going on, basically, in each and every individual stack, what I'm showing out here, right? From the backlight, the polarizing film, different kind of color filters, different nature of polarizer. And this is how, just to take you back in a history, how Rajesh and I got connected. Menavi has some very smart ideas about how we can go and deliver a much better efficiency. So definitely, I'll recommend to also chat with Rajesh. But feel free to drop me a note. We can talk at length. I'll be happy to cover more in details.
I would also add that this is actually an important problem for energy consumption, because as we know, displays, our phones die pretty quickly and we have to charge them. And there's so many phones now that they're starting to make a dent in the energy utilization landscape. So
absolutely,
definitely an important problem to solve.
Yeah, it's all about sustainability, and I don't have the data on top of my head, Rajesh. So we care, obviously, or the industry is becoming more and big about the climate and the sustainability and amount of energy we consume. And just knowing the 95% of that's being thrown out, any little drop of saving, as you said, would go and help long way in our sustainability mission. So absolutely, a lot of opportunities.
Sriram had a second question, which is that.
Yes, on the pixels. Yes, so we'll cover a lot more into that, Sriram. And what exists today is a typical pixel size, if you look into the phone, is about 25 to 30 micron, basically. And this is a sub-pixel size, I should call out. But as you go into the region of applications like virtual reality and augmented reality, I will show you some of the data where the things goes under 1 micron. And that's one of the most emerging and most fascinating piece for, especially for the technologists like us on, hey, when you go down from 20 micron, under 1 micron, there is this whole different physics and the light works. And I have one specific example on some of the optical technologies that goes and help drive some of the opportunities under 1 micron. So hold on to that. If I don't answer in more detail, feel free to bring back again.
I have a quick question.
Sure.
Hi, this is Anabil. So it looks like in the LCD display technology, 5%, 5 to 8%, we can use it, and the rest is not used. So I remember a few years back, Sony started using, so in the XLED display, you can see the blue RGB. So
Right.
they started using RGBY, and they
Sure.
use the laser. So laser
Yes.
is already polarized, so you don't have to throw off like 45% light right there, right?
Fascinating.
So that way, and I think some of the Sony those projectors, they are
Right.
using RGBY laser, and they are using a prism to combine that,
Absolutely.
combine the all 4 lights, and that way it's energetically efficient, I believe.
It's absolutely very efficient, but it's missing one fundamental need. And the reason why I didn't made it to stuff like phones or tablets or TVs and stuff. Remember the days where we used to have a DLP visions? This was a digital light projector technology, and that eventually got taken over by LCDs. And the reason why that happened, Annabelle, was really about the projection is you are increasing again the form factor. You got to project it out at a certain distance. The lasers they get hot. You need to have a very tight alignment. So for example, when you drop the phone, and if there is even a smallest misalignment in the laser, basically your display is completely ruined. So driven by those factors, right? And that was that other 1%. We are covering the 99% of a technology gamut, but that still exists. You are right. The RGB laser in some of the in the projectors today, and some of even on the AR glasses. For example, the Google Glass had a laser-based projector basically, and if you look at the design, was really fat. As a user, we don't like it. We want something which is thin, elegant, lightweight, reliable, right? So that's where LCD was able to capture the market. When you look at across the dimension, especially in the mobile category, the one which is of more interest. The interest, I would measure the interest on the level of impact it has on the human beings. That's what I measure the impact on. So you're absolutely right. In your there exist other technology called DLPs and the laser base, which are more efficient, but they didn't made it to a product because all the issues I just talked about.
I'll also add to this that coherent sources like lasers have speckle, as many of us know. So speckle, unfortunately, is not very pleasing to humans. So it's something we have to get rid of in the case of displays, and it's a problem that you have to solve, and that adds complexity and cost and things like that. I see the poll is closed, so should I?
Okay, yeah, please. How does it look like?
Let me share the results so everyone can see.
Oh my goodness, there you go. Very smart crowd. I see 10 times the soccer field, right? 40% and 200 times the soccer field. Oh my God, 2000x, 20%, wow. Guys, think about a perspective. Thank you for voting. Let's look at the answer here real quick. Let me go through the slide here. All right, so 180 was the closer answer, right? So near to whoever voted close to 200x, right? So this is what I'm showing you guys is one of the example of a Gen 10 planned from Sharp. This is a top line view basically, and the area equates to around 180 soccer field. This is where your TVs are coming out, guys. So if you look at, again, the dimension perspective, we are talking about the meter square size of a glass, a factory that actually rolls around this entire gamut. It's very fascinating. If you guys ever get a chance, it's one of the lifetime experience on seeing how this big glasses move across. And this is all done without any human intervention for most part, because we want to keep the particle count low. We call out about a 10 ppm type of a clean rooms. So this is all very automated, and it's fascinating to see if you ever get a chance. But just to give you guys a perspective about the manufacturing and economy of this field, it's huge. It's fascinating. So good job, guys. Wonderful. Let's keep rolling over here. So the next I want to go talk about is the other class of a technology, which is emissive, and this is strongly erupting. As I mentioned about, if you look at the current phone market, just of last year, from a shipment perspective, there are more OLED phones in the market than LCD. So this inflection happened after LCD dominance for nearly about 2 decades, and OLEDs are breaking through. And one of the fundamental reasons for OLED is the visual quality, the fact that you can make it thin and flexible are some of the attributes. You are seeing all these foldable phones and foldable laptops. That LCD is very difficult to do. I won't say nearly impossible, but you never know. The breakthroughs can come through in an incumbent technology as well. So to give you a perspective about how OLED works, right? So this is on the left is a stack diagram of a different materials that goes in building up an OLED. So you have there's multiple layers. You start out, just think of it as a diode. You have a whole injection layer, and then you have in the center an emission layer, basically red, green, or blue. And then you have an electron transition layer, basically. So you have basically, it's a HOMO and LUMO. Basically, you have the carrier that gets into it, and that's where the excitation happens from the electroluminescence perspective. So a real fundamental principle about a century old on how OLEDs, how the LEDs typically lights up. The beauty of organic material is, as you guys see on the bottom right, basically, this are organic material. You can actually you can spin coat it. You can spin coat across the meter size glass, basically, and you connect across basically the metal layer, your cathode and anode, and boom, it works, right? So a very simplified technology. It's a self-emissive, no backlight involved. And as you guys can see, we were talking about a 95% inefficient technology like LCD. This can get you, I won't say near 100%, but I would say like it's getting close to about 70 to 80% efficiency, and it's getting better and better. Still a lot of work to be done, and we'll talk about some of the challenges. But a real simplified principle about why OLED and the fact that it's organic. You can coat it basically on the plastic. I'll show an example. People coat it behind the islands and put it in. It's a biodegradable element, so a biodegradable material. So a very interesting technology on OLEDs. And some of the challenges, so this is a state of our art. Some of the references over here, it was just talked about in a recent conference over here. So fundamentally, very simplified technology, still tons of challenges remains. So one of the top one is the burn-in. So here is the real image of an OLED TV, wherein you have a news reporter obviously talking through, not moving. So what we call as a burn-in image, you have, if you place in an image for a longer period of time, the OLED has a characteristic of drifting, basically, in terms of its performance. And that's why you see this ghosting issue, which is not good. This is the burning effect. And that's also connected to the luminance over the lifetime, wherein you basically, it degrades over a period of time. I can tell you a story. When I started working on this technology, we were building TVs back in Samsung. And I used to go and present in a conference. This was the very early days. And we used to keep like 4 TVs across 8 hours of our conference time, because every 2 hours, basically the lifetime of the TV would decay and we'll have to go switch over. It was that much of fun 10 years back. Now you see that product from LG and others. You can go buy the TV. So that's how the industry have progressed over a period of time. It's still not there yet, but it's progressing well. The another aspect, Rajesh was talking about, some of the visual fidelity is very important. So OLEDs are very thin stack material, and you need to manage the thickness really well. We are talking about 100 to 200 nanometer of a thickness. So if you now think about a meter square glass, and you need to maintain the margins of hundreds of nanometers across the glass. And when you try to have that imbalance is where you start seeing the color shift. So for a user, when you see it from the side, you get different colors, which is really annoying. You don't want that. So a lot of work going on in this direction as well. Light extraction, this is another topic. Again, as I just mentioned, these are the thin stack layer. We are talking about hundreds of nanometers. So the light gets trapped. It's very hard for light to completely come through from an extraction standpoint. So a lot of work on a cavity creation that goes along, which is a status quo right now. And we'll talk about in some of the emerging trend, one specific example on how some of the recent research work is addressing this issue. The last one, again, very critical as we are seeing this flexible and rollable display. You need to have a polarizer that's flexible. Again, the polarization principle is defeating the physics over here. When you try to change the shape of your the polarization axis, but you don't want to alter the direction. How are you going to go do that? Especially in the devices like this flexible and rollable systems. That's waiting for the breakthrough. So tons of challenges, tons of opportunities, guys. And I picked this one given the optics class and optics interest. There is a lot of room over here to improvise and help out this $140 billion industry.
Could you, quick question and maybe a comment. The item 6 on the circular polarizer. So for an OLED, you don't need the polarizer to turn off the pixels typically. So I assume this is to prevent the ambient light from causing glare and going into the system.
Absolutely, exactly right. Exactly right.
So do you want to say something about it?
What's that?
Do you want to just say a few words about this problem? I know it's a big problem. So
it's a big problem, and I would love to get rid of a polarizer. But the visual fidelity, exactly what you mentioned, right? You have this multiple layers, and we'll talk about one specific chart on what I call as an ambient contrast ratio, which is very important. The contrast ratio by itself is meaningless, but you have all these lights coming in basically, and it creates this reflection, and it completely kills the visual fidelity. So the people, for the OLED screen, they have to place, excuse me, the circular polarizer just to make sure you're controlling all those ambient light effects being generated out of the different layer stack itself. So it's still a practice, Rajesh. Again, there is a lot of work going on into that. There is not a solution. Maybe you can help the industry to break through, but it's a definite problem. And this is one of the fundamental bottleneck. You guys don't see what we love to get through a rollable product. I mean, think of it. You can roll your tablet basically, and you can bring it back in like a newspaper. And you can place it in, you roll back in and you place it into a pocket. When this is the kind of direction where industry wants to go, but this is a real problem. I don't have a solution, Rajesh, if that was your question, but I'd love to get one.
Thanks, Kunjal. No, I just wanted to point out the problem and where it comes from. Wei-Lu, who's also a professor in our department, has an important question. So I'll just read it out quickly. If I remember correctly, the organic material for blue light emission is a bottleneck for the lifetime. What is the current lifetime of the blue emission?
Great question. Yeah, nailed on the spot. So blue is still an issue. We are looking at a lifetime. So the way industry measures a lifetime is the time when you start turning on your display and it decays to up to 50%. So the number of hours for certain amount of brightness decays, it's what we call as a lifetime. For typical blue, we are somewhere around 5,000 to 8,000 hours of a lifetime.
And just to
give you a
clarify,
perspective,
the physical principle of degradation is it primarily from photooxidation? I know your training is a materials, so I'm curious the
right.
physics of.
No, it's a defect creation, exactly. It's a defect creation within the native material itself, Rajesh and Velu, basically, which creates all these defects. As soon as there is an electrical activation, basically, you have all these dangling bonds that starts breaking through under the stress, and which is not the case for red and green. They are a lot more stable. To give you a perspective, those are in the range of 50 to 80,000 hours. And the blue is the real bottleneck. You're right, guys, absolutely right. And one of the reasons, basically, and I don't have it in this presentation over here, but the efficiency of a blue, if you look at, and this we are talking about the internal quantum efficiency, about 25%. Red and green are near 100%. So you're dealing with a very low efficient material. So you need to have a very high injection current in order to go activate that, which also act as a virtuous cycle of a defect mechanism into it. So it's still a problem. And that's one of the reasons why this issue like burn-in, number one, what you're saying, it's primarily because of the blue decay happening faster than red and green that happens. Okay, does that help?
Yeah, let's keep going. Yeah, great.
All right, so I'm just watching out in time and you can keep me honest, right? And we are on to our next poll. I think I love the interactive audience and I want to keep that, momentum up, going up, right? So here is a question, right? I think someone asked me about the pixel, right? And I want to ask back that question about, hey, when Steve Jobs came out, that's the picture on the right, and introduced this marketing term I call as retina display, right? That exists in the phones. When you go out the iPhone, you will see this term and across the Apple products. What does it mean? What's the typical number of pixels in a smartphone? So you got 4 choices here: 1 million, 10 million, 50 million, or 100 million. So go ahead and do that. And in meantime, if you guys have already voted, if there is a question or additional question, I'm happy to walk through.
We'll give it a few seconds.
Sure.
Almost there.
And Rajesh, you said I can go until 12:45. Is that what? Or I should cut it in 10 minutes?
That might be extended. Well, I'll cut you off.
Okay.
Go as much as you want.
All right.
Okay, I think we have almost 90% participation. So I'll share the results. Hold on.
Wow. All right. We got 9% as 1 million, 41% voting 10 million. We got 27% 50 million, 23% 100 million. Wow. All right. Cool. So guys, the answer on the phone side is actually B. So wonderful. You got majority audience being on striking spot on. So congratulations on that. My next question basically, and we'll look through is this going to be sufficient and how do we know, right? And let's go to the next slide, is where I want to give you guys a little bit of a familiarity with the pixels, and hopefully I can also answer the question that was raised before about the pixel size, right? So in a definition, this is one concept I want you guys to be familiar with, visual acuity. And this is basically how can I, or what's the maximum number of pixels you need to basically for eye not to discern any artifact, right? So you're seeing all this 2K, 4K, even 8K, talk about the TV, then that takes you up to 1 billion pixels. So phones are 10 million pixels, your 8K TVs are 1 billion pixels, just to give you a perspective of how the things are rolling. And this field becomes a lot more important, guys, again, from a product standpoint. So the one on the right, what you guys see are the two curves at a different PPI. So PPI are pixels per inch. So more the PPI, you have more denser pixel. And this the right side or the axis is basically arc minute. So 1 arc minute is typically your 20/20 vision for a healthy human eye. So the eye can able to distinguish up to 3000 PPI for about nearly 3-inch type of a display. And if you have a lower PPI, you need a larger size. So it goes up to 8K inch. So think about it when you're building a VR, basically a VR display or an augmented reality display that needs to fit right within your eye box. You need to have a very high PPI. And that places a stress on what should be the dimension of a pixel. So 20 micron for phones today. And you need to go at least 3 orders of magnitude higher, or even 4 orders of magnitude higher, in order to break through into this AR and VR technology, just from a display perspective. So just give you a gamut about where the things are heading when it comes to applications like VR and AR. Okay. The next concept I'm going to go a little quick now, but feel free to interrupt just for the timing reason. The other concept I want you guys to be familiar with, and Rajesh has that question about like, hey, why we need polarizer for OLEDs? You don't need it because these are self-emissive pixel. So if you look at basically the TV example over here, so there's something called contrast ratio, which is nothing but white over black levels. And OLEDs are known for a very deep contrast ratio because it's a native, you can turn the pixel black or white, right? So when you walk into a Best Buy or a Costco, you see this marketing literature about, hey, a very high, perfect black, right? I took this picture out of Costco. Basically, they had LCD and OLED TV side by side. And the question I asked basically, hey, is higher contrast ratio better, right? The usual, it's yes, but the question back, when someone tries to sell you basically this, you should go back and, hey, tell me about the ambient lighting condition, because what matters is this reflection that comes through. So in a typical environment, like I'm sure what you guys are sitting or where I'm sitting, there is always an ambient light. And you see this reflection at an end of a day that creates this noise floor on the black level. So the way to explain this in a more experimental terms, so what you have an LCD display, which is twice the brightness as OLED, but OLED got like nearly 2 orders of a better contrast ratio. So at a low luminance level, this goes to 200 lux. But if I had a data under 200 luminance, the OLED would actually behave much better. But as you keep on increasing the ambient lighting condition, as you guys can see, OLED really watches out. So even though it has a higher contrast ratio, how this marketing literature is, but it's really about under what condition and what scenario you're operating. So just want to help you guys with a concept on how this different optics comes in together when you think from a product perspective, what is important to the user. Yeah.
So just to clarify, the idea of using a circular polarizer with the OLED is to essentially cut down that R1 reflection. Actually,
that's exactly right.
Yeah,
that's exactly what it's
R1 and R2. Yeah.
Yes, that's exactly right.
And so essentially, if you want to use your phone under outside in the sunlight, this LCD is in a sense better.
Yes.
Okay.
Though I would be biased, I'm an OLED guy. I would be biased about the OLEDs, but the short answer is yes for now. All right, so I want to give a quick flavor on the emerging technologies, basically. So we learn about the concept. I think we learn about some of the principles to help you arm with when you guys go for shopping. The Thanksgiving's coming, whether it's a TV or a phone. I hope there is. You guys are smart, but at least you can start asking those questions about, hey, what pixels, right? What resolution? Why not high resolution, right? What kind of a contrast ratio? What does this black level means? Let's take a step ahead in terms of what's coming next, right? And I took a couple of articles, which is this is an article that came out like last month from Science. And I know Rajesh is very deep into the field. By no means I'm an optical expert, so feel free to chime in, Rajesh, as well. So what this research group between Samsung and Stanford just released a report on what they call as a meta-surface-driven OLED display beyond 10,000 ppi, 10,000. So if you look at phones today are about 500 ppi. So this is 20 times more density of a pixels. And this guys took a fundamentally different approach on how they do that. So in a real nutshell, and I'm sure Rajesh can add a lot more value here than I do, but they use this what they call as a meta surface. So meta surface are basically, these are the nanopillars basically, and they are nothing but in my dumb definition, they're the optical modulators. So you can even change the polarization of the light, and even you can change the phase basically. And what these guys did basically, they here at the left is a cross-sectional view. So typically in the OLED, you will actually take some kind of a pattern to draw red, green, and blue. What these guys did basically, they took the light, basically they reflect it through the meta mirror. And depending upon the optical or the pitch between the two arrays, so it's about 80 nanometer diameter. And depending upon the pixel pitch, you can actually go and generate a different wavelength spectrum. This is how they came out with red, green, and blue without the need of a fine metal mask pattern, which is fundamental limiter of why the today's phones and stuff are stuck at 500 to 1000 ppi. So they fundamentally took 10x leap by this technology innovation by driving the meta mirror into the structure. So to give you again a question on the pixel density, pixel was asked. So this is a typical 20 micron size that exists today in cell phones. As you go into the VR and even the AR, you need to go drive more than 10,000 ppi. So this was one of the great breakthrough, or one of the interesting breakthrough I should call out. And what do you think, Rajesh? Being in, I'm sure this is something you are very familiar with. That. I'm sure you'll have a creative ideas to even do better than that.
I have some opinions of this paper, but maybe that's for another time.
I'm sure. But
it's definitely very interesting. Yeah.
Yeah, but this definitely gives you a perspective of where the research excitement is, guys, coming out in the Science journal. So why this field is so dynamic and so disruptive, basically, in a space of what needs to be done, and we are not even halfway there. The other real quick, I want to give a quick view on what I call this micro LED display technology. And this is something that's near and dear to my heart. And the reason for that is what we are doing here in this is also an emissive type of a display. So we talked about the organic OLED. Now let's talk about inorganic OLED, inorganic LED, sorry. And these are the LEDs that exist on a wafer. I mean, think about a world wherein companies like Intel have the best-in-class performance on a wafer, but it cannot scale. We just talked about, in order to scale, you need to be in the meter squared glass, the one on the picture over here. How would the world would look like if you can get the performance of a wafer that exists on a wafer, but at the level of a glass scalability, so that you can go drive into realistic products? And that's exactly this field is. This is about 10 to 15 years old, where the definition of this concept were brought in, especially from the professor Rogers group in University of Illinois, Urbana-Champaign, when he talked about this concept, and there is a lot of research excitement in this space. So the reason I'm deeply connected to this field, again, at an end of a day, you can drive a very broad spectrum. There is no one technology that fits all, and maybe this is the one. What I call as is this an ultimate display? So you see the one on the left about the projector, the LEDs that being used for decades. People have known this. You use LEDs in a backlight. Then you have this something called mini LEDs, basically that goes into the video wall. So this is like one example of a company called Innolux. They actually created like a 75-inch TV by driving or shrinking the size of the LED. The one on the right is the video wall, basically from Sony. What they did, basically, they just tiled the small pieces of this micro LED display and created like almost 100-inch basically a television out of it. So these are pictures from the roadshow. You can see my screen, right? There's a guy here who is pointing at the screen. So it just gives you a gamut of how big it is. But it's not stopping here. The key part is like, hey, how can you go beyond that dimension? And this is a picture from one of the startup called ViewReal, who was able to demonstrate about 30,000 PPI. And there is a startup here in Bay Area by the name Mojo Vision, who has integrated some of these pixels, basically, this is the cartoon, into the island. So they want to create a full 3D AR experience without wearing glasses. So it sounds gimmicky, but this is where a lot of capital injection which is going on. So it gives you a perspective of the micro LED field. This is a very new category of a display. It's not completely done yet. It's actually at a beginning phase. So really a really good field to jump in looking for disruption. Okay. Any questions?
Are these all organic LEDs based?
No, these are all inorganic LED. There is no organic LEDs here. This is
like 3 nitride.
Gallium nitride. Yes,
three
it's
nitride.
on the
Okay.
Right, exactly right. So very fascinating space, looking for a lot of disruption.
Yeah, and just to add to this is also the epitaxial liftoff process from the Rogers group is really enabling a lot of this, because now you can do wafer level processing. Otherwise, it's very expensive.
Exactly right.
So Sriram,
exactly.
you are you are the expert in this.
Right. The
oh my God.
reuse of substrates, and yeah.
I would love to talk with you, Sriram, but this is we have some very interesting work going on at Intel as well. So, and I'm sure I can take a lot of help here.
and I just want to point out, we should probably wrap up in about less than 10 minutes.
Okay, I think I'll be done in like next 3 minutes. This is my second last slide.
I have a quick question, if you don't mind. So,
yeah, please.
So you're talking about RGB, but if I understand, to get a extended or better color gamut, we need Y also, right? So,
now RGB and yellow. Okay, now I hear you. You're absolutely right in your comment.
Now there is a well-known green gap with the not efficient green and yellow LED.
Yes.
And still some research going on. So if you can comment on this.
I would say I'm not very qualified on talking deep about the green gap. It just, I don't come from a gallium nitride field. I've known from my team about the issue, and it's an issue for a longest period of time. What people are working around with that is an excellent question. People are working out with a different structure. So they are using a blue LED, which is obviously the on a gallium nitride is the best status quo available today. And we are using something called a quantum dot material in order to go create a red and green color. So rather than using a green micro LED or a red micro LED as a start, the industry is starting out with a blue micro LED as a base. and placing the quantum dot filters on the top of it. So, but this is a start. I don't like that approach, to be honest.
Yeah, they earlier also used phosphor, but
that's correct.
Conversion. Yeah.
That's exactly right. So this is just, I call it like an incremental improvement. The continuous improvement are good. What the holy grail would be, hey, how can I get a native red, green, and blue? What would be even fantastic if we can get red, green, and blue on a single wafer that I can go and transfer rather than waiting for 3 different wafers. So the question, I'm sure we have a big expert over here. You can do green and blue on a gallium nitride wafer, which is very recently demonstrated five years back. So if you guys are more interested, you can look for a company named Aledia, which actually is an Intel investment into it, the one I drove as a part of my collaboration with Intel Capital. There is another company called Glow. They're based in Bay Area, but the fundamental, some of the research connection goes back in Sweden. So both of them demonstrated red and green. The blue still comes from InGap, basically. You still cannot do red on the gallium nitride wafer. So again, lot of depth into, lot of details into it, but the green gap issue exists. The industry is looking around various ways on how I can go from a product perspective to bring back in by using blue plus quantum dot filters. All right. So guys, the message I have, right? This is we spoke about technology. We also talked about basically some of the product intercept, and this is a journey. And you look back, basically, this is like a last 20 years of a map. Rigid, you got fixed, you got curved, you got half foldable, you got foldable, rollable. We are still in the middle. There's a lot needs to be done. We haven't even gone and talked about the transparent display or a 3D holographic displays. Man, this would be a holy grail. Man, how awesome would be is you have a live person image sitting right in front of you. We are all stuck with these 2D screens today, which is not how we want to live. And how can we get there? So lot needs to be done. We are still halfway. I want to quickly touch about work, what I do at Intel. Obviously, I cannot talk a lot more into detail about it, but I work on all the stuff at the last end I spoke about on some of the emerging trend, and the goal really here for Intel, especially in the PC space, about how we can go drive a better battery life. So we talk about the 95% inefficient LCD display that still exists in bulk of a laptop. How can we make it immersive in this holographic standpoint, and some of the form factor evolution around the flexible and rollable displays. So with that, I think I would say stay in touch, right? Got my email, connect over LinkedIn. There is this large society, if you guys are not familiar with the Society of Information Display, which is a large display community. If you guys are more interested into it, feel free to go and join. So with that, Rajesh, sorry I went over, but you have a fascinating crowd, very, very, very interesting questions. The floor is yours.
Great. Well, thank you so much.
Kunjal, sorry, I had one question.
Lots of questions here. Go ahead, Advait.
Sorry. So you just showed us a PPT on Mojo Vision, which had these nano LEDs. I mean, it's fascinating how you can put a display on top of an eye.
It's a contact lens, isn't it?
It's a contact lens. Yes, it's a contact lens.
Yes. So can you comment something on the nano LED technology?
Other than the fact that you can make it, and it's still TBD on terms of people using it, right? So from a technology standpoint, we have a reports in within Intel, which I cannot go a lot more into detail, but you run into the issue as soon as you go do the mesoscaling. you have all this defect creation that happens, especially with the gallium nitride, and the performance really goes down. And that's today, it's a fundamental issue. There's a lot of research going on how you can go passivate the wall in order to make sure that you're not losing up the performance. When LED are the best efficiency material, that's why we use LEDs in our home and all. But as soon as you go down from 200 micron under to 1 micron, that's where all the defect creation happens, and you lose all the good efficiencies over there. So it's a good prototype. It's a good demonstration of the physics right now. There's a lot more improvement in terms of what needs to be done, especially from the efficiency improvement. In terms of how are you going to go access the pixel, basically, how are you going to go communicate the pixels when you need to have a medium for communication? How are you going to get some of the other electronics in beyond just display? So these are all some of the important problems over here to solve.
Yeah,
Thank you.
That's a great question, by the way. And I should also point out, these are really system level challenges, really right in the middle of electrical engineering. So, and it's interesting that, you know, I'm in electrical engineering, and Kunjal is a material scientist by training, but, you know, it's so interdisciplinary. We need so many different backgrounds. Neda has a really useful, interesting question. Neda, do you want to say it, or do you want me to read it? I can read it if you want.
Yeah, either way.
Go ahead, go ahead.
Now, basically, I'm talking about the innovation aspect of the technology in display technology. Is there any effort or at the level of conceptual design to factor in the properties of our visual, the human natural vision, like visual sensitivity or visual perception, into the design of these display technologies? Basically, the idea that we know that the input to the brain is different from the output of the brain. This is the things that we perceive is not the things that really exist, or the way they exist is different from the way that we see this. Is there any innovation effort toward this direction at all?
Oh, I see Kunjal left. So actually, this is it's a relevant question to my research. So I can say a few words first, and I'll let Kunjal answer. But this is a very important problem in something called holographic displays, which is different than what Kunjal talked about. Kunjal talked about actual physical displays. But in holographic displays or three-dimensional displays, you have this issue of your eyes are focusing on a plane, which is this LCD plane or OLED plane. However, your brain is actually perceiving a three-dimensional scene, which can occur from many reasons, because you have two eyes, you know, you try to binocular vision, so 3D movies. And this is highly problematic for human brains, because remember, our eye is focused on a single plane, but the brain is perceiving multiple planes or 3 dimensions. And this is what's called a convergence accommodation conflict. And this causes lots of problems in virtual reality, augmented reality systems. So for instance, I can't wear an Oculus headset for more than 5 or 10 minutes before feeling sick. So this is a problem that you solve both with a mixture of hardware and software. So in other words, you have preconditioning of the display data that you can do and present to the eye. But at the same time, you have multiple focus systems, like in the example of light field display, holographic displays. Kunjal, you saw the question. Do you want to say?
That was an interesting example, but yeah, I mean, that was one thing, that the depth perception and this binocular vision. The other things could be like our perception of color, our perception of motion.
Yeah.
The temporal and spatial sensitivity that we have. I mean,
so color. I know color blindness. There are some solutions which are driven by displays and software. So that's a very, very interesting example. Go ahead, Neda. Sorry.
No.
That was a matter of question. That is there any eye movement? So, for example, our eye movement is affecting our perception. I mean, if the way that the images that project to our brain during eye movement is the same as the camera, moving camera frames. Okay, those images captured by moving camera, these are the input to the brain. but we do not see the world at all like this. So brain is constructing the visual world for us. So that could be like the color and the motion. It could be the object recognition, face recognition. All of these are basically what brain construct. Is there any things, any activity or concept toward making it more brain compatible, making display technology brain compatible?
There is the Artificial Eye Project, right, which has been funded by the NIH, I think led by University of Southern California and others, where for blind people, by essentially stimulating the retinal nerves or nerve ends, which are apparently damaged, you can initiate experiences in the brain, particularly with color. I think the resolution is relatively low still, but that's one example that I can think of. But Kunjal, do you know anything related to what Nate is asking?
Yeah, I think with some of the stuff on this, what we call as the brain, this brain imaging, basically they're trying to fit in, I won't say displays yet, and this, the closest they could come through was the contact lenses, which still has, it's other challenges on basically on the eye safetiness and stuff like that. But I wasn't aware, Rajesh, about this artificial eye, so that's what's good to know. A certainly fascinating question.
That's primarily aimed at blindness, congenital blindness. Also, of course, there's Neuralink, Elon Musk's startup, which I think is trying to do something similar, but I'm actually not familiar with it. Neda, you probably know this much better than either me or Kunjal.
I'm curious about industry. I mean, in academia, in research, Neuralink stuff, we know that there are some efforts, but I was more of the industry type of effort over that. Thanks for the examples that you provided. It's very interesting.
I had a quick question. Could you comment on the market share of organic and inorganic LEDs in displays?
Yeah, great question. So what it is today, I would say a larger proportion, if you look at an entire display spectrum, about, I would say 95% of, you said OLED and LCD or organic and inorganic? Is that what you're...
Like basically nitrides based.
Oh, okay. Oh, I would say, from a display application perspective, inorganic LEDs are minuscule. It's like less than 0.5% maybe, I would call out. It's all OLEDs. But when you flip it around for a lighting application, that's where you see LED is a vast majority of our market. OLEDs are still breaking through. And as I talked about some of this reliability challenges, right? Especially about the temperature, when you're dealing with the lights, basically, who needs to be turned on for a longer period of time. They're still coming through. They're not there yet. And then automotive industry are putting lights, the red tail light, basically, which are OLEDs. So Audi actually launched it a few years back, and they were charging crazy premium just for doing that. So for display application, it's 99% OLED, 1% inorganic LED in a very handful of application today. But from lighting application, it completely flips around. You got most of it as inorganic LEDs, and the organic LED being under 1%.
Great. I'm afraid we are way past the time, and I'm not supposed to keep the students so long. So this is very, very exciting. And thank you. First of all, thank you all for the audience and the fantastic questions. And second, I'm very grateful to Kunjal for his time. And hopefully everyone learned something new today. And you have his email and his LinkedIn. And as he said, connect directly with him. I know Intel is hiring for sure. And I know they do fantastic
research. Yes, please. We need smart people.
Some of the students here are probably going to be looking for jobs in the next few years. If you're excited about working in this field, definitely reach out to him or me for that matter. Great. Thank you
Thank
all.
you, Rajesh.
I will.
It was my privilege. Yeah.
If you don't mind, Kunjal, is it okay that I post the lecture, the seminar?
Yeah, that's fine. Yeah, just go ahead. I send you the PDF. Maybe the
I will share
PowerPoint was
that.
too that. All right, no worries. All right, thank you, everyone.
Take
Goodbye.
care, everybody.
Yeah, bye-bye.
Happy
Bye-bye.
Thanksgiving.
Yeah,
Happy
thank you.
Thanksgiving.
Bye.
Yeah, bye-bye.
Bye.